Okay, so this is an experimental question where they're giving you a setup and some gathered data and asking you to connect it to theory, essentially. So part A doesn't even really use the actual data yet. All it is asking us to basically relate the energies before and after, where before is when we've pulled the spring back, and after is sort of the instant it passes through the photo gate. And so we just got to think about what energies are present. Well, the thing's perfectly horizontal, so no gravitational potential energy really matters. Well, so that doesn't apply. When the spring is stretched, though, we have spring potential energy, right? So we're going to say that the initial energy equals the final energy. And initially, the spring is stretched. There's a 1/2 k x squared, where x is what we're told is that's the extension of the spring, and k is the spring constant, which we know that number as well. And nothing's moving, so there's no kinetic energy, not rotating, not translating. Afterwards, once the glider passes through the photo gate, the spring is now not stretched at all, so you don't have any spring energy left. But the thing is, the glider is translating, so there's kinetic energy. There's no rotational stuff happening, so that's the only kinetic energy that we have. And so this right here is all part A is. It's just recognizing what energy you have before, what energy you have after. Part B, we're told exactly what we need to plot. We aren't really told why, but we're given data, x and v, and we're given some results from, or calculations from that data, x squared and speed squared. And so this question is just plotting the data precisely, right? That's all it is. You don't have to reinvent the wheel here. It tells you exactly what to do. Label the axes, include the units, and the scale. So I'm going to do that. Note, however, there are two options for how you plot this, because it doesn't tell you that you should put either one on the x or y axis. How it's written implies that x squared is going to be on your x axis, so that's what I'm going to do, but if you did it the other way around, there's nothing wrong. So this is x squared units of meters squared. This one is going to be v squared units of meters squared per second squared, right? And so now we have to figure out how to make the scale fit sort of the plot area, and using as much of it as possible. And so if I look at the x-axis, there are 6 sort of big tick marks, and we have to go from 0 to basically 2.5. So I did every big tick mark to be 0.5 times 10 to the negative second. And so on. All right, if I do all that, then it works out pretty well. There's only one tick mark that I don't use, but I can't really space it out intelligently any better. And so on the y-axis, we have to go from 0, I should make it clear, this is like 0 there. That's 0, oops. Right, that's 0, 0 is that point. So on the y-axis, we have to go from 0 to 5, and we have 5 big tick marks. That one's, I think, a little bit more straightforward. Actually, I need to respace that. I don't think I drew that quite right. 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 And so that's what they mean by label the axes, including units and scale. I've labeled what goes where, right? What am I plotting? I've given it units, and I've labeled sort of each tick mark appropriately, and I've used the whole space. So now we need to put the data points on here. And that's just as simple as reading off the data table and sort of plotting carefully. So I'm not going to do as careful a job as you would need to here, because you have each of these big tick marks is divided up into 5 by 5 smaller grids. So you need to plot as precisely as you possibly can. But since I don't want to redraw every single one of those tick marks, I'm only going to do sort of approximately right. point down there, another point kind of down there, another point about there, another point there or so, and the last point is like there. So again, you have to plot as precisely as you can, but once you do that, it's just putting the data points that you have, no calculations or anything necessary. And that's part B. Part C, draw a best fit straight line through the data. Again, don't reinvent the wheel. You know sort of what's going to happen. You just need a straight line that connects all these points as closely as possible. And again, you would have a straight edge for this. So I expect a perfectly straight line. I don't, so it's not going to be quite as perfect, but the general idea will still be right. It's going to look kind of like that. And you wouldn't expect every single point to be on the line, right? Since I didn't have perfect graphing, I kind of just drew where I knew they were going to be, but some of them are a little bit off. And that's kind of what you'd expect. The goal is to make it straight and go through as much as possible, all of them. All right, and so now C part 2 is where we start to go back to doing some physics. We have to connect parts A and what we did with the graph together. So right, this is a plot of x squared versus v squared. We have an equation for part A that has x squared and v squared in it. So if we wrote that equation from part A in a sort of y equals mx plus b form, right, we get v squared equals, right, the 1/2s cancel. So we get k over m x squared, right? And so this, right, if we sort of match pattern stuff, is like y equals mx. And so this tells us that the slope is related to the mass. And those are different m's, just to be clear. I'm using m in the bottom one, the blue, for slope, and then the top it's for mass. So I'm just going to write slope from now on to distinguish. But this is the key relationship, is that for the graph we have, there's a relationship between v squared and x squared where the slope is going to tell us the mass. So we know that the slope equals k over m, or m equals k over slope. So if we can figure out the slope of that red line, then we can calculate the mass, because we know k. And so this is another important point. You have to pick 2 points on the line, not 2 data points. 2 points on your best fit line, right? It says use the best fit line. So the points I'm going to pick, easiest one is 0, 0. So I'm picking that point as one of my points to calculate the slope. The other point I'm going to pick is like a one that's like right here on my graph, and this is right, 0, 0 is on my red line, and this one, again, not perfect on this graph, but I'm going to write what it was on my real one. Right, is that value. Those are 2 points on my line. So we can calculate the slope, right? Delta y over delta x, which is 3.1, 1 point. That's again really sloppy. Right. And if you calculate that out, you get a slope of about 207. And then we know that m is k over slope, which is 40 over 207, which works out to be about 0.19 kilograms. And that's your answer. As with all things, if you do a different best fit line, you will get a slightly different slope. That's fine. There are definitely bad best fit lines, but there's definitely a range of good ones as well, depending on which points you try to get closest to and which ones you don't. So this one is a reasonable answer. I think they said that you would be allowed to get anywhere between 0.18 and 0.23 kilograms, something like that. So you have a wide variety. Just whatever line you get, just use it, right? And if you calculate the slope and don't know what to do with it, that's still something, as long as you know it's kind of related to the slope. So that's part C. Part D is tricky, partially just because I think of how it's drawn. So the first thing we have to do is we have to write a new conservation of mechanical energy equation. So it's going to be like part A, but a little bit more complicated because now we're at a slope. So gravitational potential energy is going to be involved. So initially, we've both stretched the spring and we're sort of high above the photo gate position. There's some height that it's going to go down. So initially, we're still starting with that. But our initial energy now is 2 points. We've still stretched the spring. That's the same. But we now have gravitational potential energy. I'm going to call this H prime for a reason, as you're going to see. We're a certain height above the photo gate. And your first instinct might be, because of how it's drawn, say that H prime and H are the same. But H is the position, in terms of height of the block, when the spring is unstretched. So if we stretch the spring a distance x, we add more height as well. So we have to figure out what H prime is, right? That's got to be our first step. And so we can do that. Right? This is how much we stretch the spring. This is, I'm going to call this one, I don't know, let's call it y, actually, because it's a vertical thing. And this is theta, right, that same theta that's in the picture. And so if we know how far we stretch the spring, and we want to figure out y, there's a relationship between those three variables, right? Sine theta is y over x, or y is x sine theta. So y is how much additional height the block is if we stretch the spring by a certain amount of length x. So that means that H prime is the original height plus the extra bit that we added, right? Namely that. So that now we can express the initial energy in terms of things we know. So I'm going to just distributing that H prime thing out. So that's our initial energy. Our final energy, however, does not change, right? It's at that photo gate's position. That's what we've defined the gravitational potential energy to be 0, and the spring is unstretched. So we just have 1/2 mv squared. Right, and so this right here is the answer to D part 1. And I think that these parts are the obvious parts. And this one I'm going to underline in blue. This is the little bit of extra trick based on how it's drawn. That's the part you have to get part 2 right. So part 2, well, we kind of know what we did to figure out parts A, B, and C, right? We wrote v squared equals something x squared, and we found a relationship. So let's try that again, right? Try to get into that sort of y equals mx plus b form. So v squared, so we're going to multiply by 2 and divide by m. So we get k over m x squared plus 2gh plus 2gx. Actually, I'm going to 2g sine theta times x. So, what do we have? When we had, right, just this piece, that was a linear relationship, right? That's like a y equals mx. If we add in this blue thing, that's like the plus b. So that would still be linear. But here's the problem. This piece. This piece means that the dependence of v squared on x squared is not quite as simple, right? This is a quadratic. We have an x squared term and an x term. So this is no longer going to be straight anymore, because if we plot this, we're going to have like plus c square root of x in this case. And so this won't be a straight line anymore. As x increases, we don't get a linear increase in y. And so because of this term, it's no. And basically you just have to show this, you have to reference this term somehow, showing that it's a quadratic and you have both x squared and x in that energy conservation statement to get the points for that. But the answer is no. And that's the whole problem.